In this lesson, we're going to look at numerical representations of functions, and particularly representations of exponential functions, but also linear functions. To start, let's consider the following tables. This would be numerical representation of two different functions, f of x and g of x. We know that these represent functions because each input uniquely defines its output, and with a table of values, to determine if it represents a function, you should first look at the input values to see if any repeat. And they both have the same input values of 20, 25, 30, 35, and 40, which do not repeat, so they clearly uniquely define their output. Now, if 20 were repeated, so you had a repeated value, you would just have to ensure that 20 went to the same output value of 30. For if it went to something else, like 35, then f of x would no longer be a function. So let's cross that out so that we can ensure that we do have tables that represent functions. These are numerical representations of functions. The next thing we'd like to ask ourselves is what kind of functions they are. And the easiest one to determine first would be linear. So let's ask ourselves, are they linear? If they are linear, they have a constant rate of change, or slope, which is the change in y over the change in x. And we would have to determine that this stays constant between each coordinate pair. So the first coordinate pair, 20, 30, and 25, 45, we calculate our change of x, which is 5, because from 20 to 25 you increase 5. The change in y would be an increase from 30 to 45, or 15. So let's calculate, and if you like, you could pause the video, but I'm just going to go ahead, calculate the change in x values and the change in y values. The change in x between 25 and 30 is 5. It's 5 between 30 and 35, and 5 again between 35 and 40. Now, the change in the y values between 45 and 60 is 15, between 60 and 75 is 15, and between 75 and 90 is 15. In which case, the change in y, the ratio of the change in y over the change of x, stays the same at 15 over 5 between each coordinate pair. So it stays 3, so our slope is 3, and we know that the function f of x can be written as 3x plus b, where b would be our y-intercept. Now, if we were given an x value of 0, that would tell us what our y-intercept was without having to do any more work. But since we're not given that, let's use a value like 20, 30 to plug it in, 30 for f of x, 20 for x, and we can calculate b. Subtract 60 from both sides, and we see that b is equal to negative 30, in which case f of x is equal to 3x minus 30. Now, in order to determine if g of x is a linear function, we again calculate the change in x and change in y and look at the ratio of the change in y over the change in x. Noting that these are the same input values, we see that the change in x remains constant at 5, which means the change in y should remain constant in order for the ratio to stay constant. But seeing this decimal out here kind of points out to me immediately that the change in y is definitely not going to stay constant. But to show this, we'll recognize that the change between 1000 and 1200 is 200, 1200 and 1440 is 240, in which case the ratios 200 over 5 and 240 over 5 are not going to be the same, and this is not a linear function. In which case, we would like to determine if it could possibly represent an exponential function. Now recall, an exponential function is one that changes at a constant percent rate, in which case, let's talk about how you calculate a percent. To do that, let's look at an example. What percent of 50 is 30? To calculate the percent, you look at the ratio, 30 divided by 50. When you're looking at percent of, that always goes in the bottom. And actually, you can rewrite this as 60 over 100, in which case we see pretty quickly that 30 is 60% of 50. Let's look at another example. If you grow from 46 inches to 50 inches in 1 year, what percent of your original height, okay, maybe not your original height, but of the previous year, did you grow? In which case, you're calculating the percent of 46. So that will go in the denominator, and you look at the ratio again of 50 over 46, which, when you plug into your calculator, is approximately 1.087. So you would grow approximately 8.7%. Now, if you were growing 8.7% every year, then your growth factor would be 1.087. Okay, so let's go back to our original g of x table and determine if it might represent an exponential function. To do that, we are going to look at ratios of the output values, or 1200 over 1000, 1440 over 1200, 1728 over 1440, and 2073.6 all over 1728. This one's pretty easy to calculate as 1.2. The rest I'll have to plug into my calculator, but I see that 1440 divided by 1200 is also 1.2. 1728 divided by 1440 is again 1.2, and then 2073.6 divided by 1728 is again 1.2. So we see we have the same result in the ratio of the output values. But what this tells me is, since the change in x is 5 every time, that every 5 units there is an increase of 20%. Now, functions typically are represented what happens every 1 unit, so we need to determine, when we write our function g of x equals our initial amount a, which if we had an x value of 0, we'd know what that was, but we don't, times our growth factor, which is going to be 1.2 to the 1/5, because every 5 years it increases 20%, or multiplied times 1.2 to the x. In which case, to solve for a, we need to, just like a linear function, we need to use one of our points. So let's use 1000. Replace g of x with 1000, with x with 20, in which case we have a times 1.2, 1/5 times 20 is 4, so a is going to be 1000 divided by 1.2 to the 4th. I try to not calculate anything until I absolutely have to, so that I'm not approximating. Plugging that into my calculator, well, as in with exponential function real-world problems, it can get kind of messy. We get 482.25, and that still is an approximation. So our exponential formula should be our initial amount a that we just solved for, 482.25 times our initial value, and now I'll actually calculate 1.2 to the 1/5, and that again will be an approximation of 1.037 to the x. So our exponential function is 482.25 times 1.037 to the x value, and that is as close as I can to getting a formula to this numerical representation of an exponential function. So now let's look at a brand new table and determine if it represents a linear or an exponential function. Let's note that this time the change in x is 1 every time, which is going to make our life easier, since when we look at ratios of our output values, we'll have our actual growth factor be. Oh, I kind of gave away that it's exponential. But at the same time, just looking at the table, you have these decimals out here and no decimals here. So it kind of points to the fact that it couldn't possibly be linear. And in fact, it's not linear, because the ratio of the change in y over the change in x was not going to remain constant. So now let's calculate our ratios of output values: 216 over 200, 233.28 over 216, 251.94 all over 233.28. And this would be a good time to pause the video and actually calculate this yourself. Make sure you get the same values that I'm getting. When I plug it in, I get 1.08 here, 1.08 here, and this one is not exact, probably because I didn't take it, it's not taken out any more decimal places, but it's approximately 1.08, in which case if you were calculating for B like we did before, when you looked at G, or in this case F of say 1 all over F of 0, by the formula you get a b to the first all over a b to the 0. The a's would cancel and b to the 0 is just 1, so you would just have b is equal to, well, the ratio of values that you looked at, 216 over 200, or 1.08. And we got lucky again in this table because we have an x value of 0, which tells me immediately that a is 200. So the formula for f of x is 200 times 1.08 to the x. We like it when they give us an x value of 0 because that tells us our initial value. The next thing that we're going to do is find exponential functions given 2 points. This is something that we've been doing for a while for linear functions, but now let's see what happens if we have to find the exponential value, in which case we'll call these e of x. And we want them to look like a times b to the x, where a is my initial value and b is my growth factor. So we'll look at our ratio again. We'll look at, and I always like to pick the biggest x value to put on top. So when I look at plugging that into the formula, a b to the 9th all over a b to the 5th, I always get a positive exponent on b. A's cancel. B to the 9th over b to the 5th is b to the 4th. Now I also want to look at what e to the 9th all over e to the 5th is when I evaluate it. What's the y value? E to the 9th is 5, e to the 5th is 2, or 2.5. So then b is the 4th root of 2.5, which is approximately 1.26. And then I need to solve for a because I'm not giving an x value of 0. So I'll pick 5, 2. I have 2 as my output value. A times 1.26 to the 5th power divided by 1.26 to the 5th power. Plugging that in my calculator, I get a is approximately 0.63. So this function is 0.63 times 1.26, oops, got ahead of myself, to the x. I need to learn to write smaller. Okay, so let's look at this one. I'll call it e of x again. So I'm going to look at e, and the bigger x value is 1 all over e to the negative 2, in which case that's a b to the 1st power all over a b to the negative 2. The a's cancel. B to the 1st over b to the negative 2 is b cubed. And then evaluating that in terms of what the actual y value is, at 1 it's 3, at negative 2 it's 24, or 1/8. So b is the cube root of 1/8, which is 1/2, or 0.5. Then I need to find my a value, so I will choose 1, 3, plug in 3 for y, finding a, 0.5 for my growth factor, and 1 for my x. So I'll divide by 0.5, which is the same thing as multiplying by 2. So a is equal to 6, and this formula is 6 times 0.5, or 1/2 to the x. So now you'll see how you have to find exponential functions given 2 points, and that is the end of this